Okay, we're going to move from a general description of spectroscopy, how electromagnetic radiation interacts with atoms and molecules, into all the specific ones that you've probably used most of them. Not sure you've used microwave, which is the first one we're going to talk about. So 11B is rotational spectroscopy. And I'll get this set up quick. Okay, so rotational spectroscopy. Let's just think a little bit as we get started here about each of the spectroscopies. So rotational spectroscopy usually takes place in the microwave region of radiation, so it'd be microwave spectroscopy. When you look at the energy it takes to change to add energy to different modes, rotation, if it's 0.01, whatever units your energy are, then vibration is about 1 to 10, and then electronic is about 100. So rotational energies are very close together for molecules, and it doesn't take a lot of energy to change the rotational energy of a molecule. So we can't be talking about atoms because atoms don't rotate. It's always rotation deals with nuclei moving through space. So we're talking about molecular rotational spectroscopy, and it's going to end up in the microwave region. So to get started, we want to think about what we already know about the energies. So spectroscopy is photons interacting, so you'll change states. So we need to know something about the states we're talking about. So if we have a linear rotor, something like H2 or CO2, any linear molecule, if we look back at chapter 8, what we saw was that the energies are quantized and that the energy values at any J, which is the quantum number, are equal to H, this B, which is a function of the properties of the molecule, and then J. So J can vary from 0 to infinity. So when J equals 0, energy 0, so your molecule can stop rotating. That'll be the ground state, and it goes up in energy from there. So this rotational constant is equal to h bar over 4 pi times the moment of inertia. And the moment of inertia is where we have the information about what molecule we're dealing with. So the moment of inertia, you sum up all the masses that are rotating times their perpendicular distance from the axis that they're rotating squared. So when you look at this picture, it's a pretty good picture. So if the bond axis between this little MB and MC right here is the axis of rotation, then we need to add up the masses of each of these green particles and each of the red particles, each multiplied by their perpendicular distance from the axis they're rotating around, and add those together. So it would be a sum of mass of D times distance D squared. So it'd be 3 of those terms. And depending on your geometry, things can get kind of crazy. So linear molecules are easy because if you have the bond length, then you know how far away from the bond axis something is that's rotating. It's easy to calculate the moment of inertia. But when you get other geometries, you might have to take into account trigonometry and figure out how the perpendicular distance relates to the angle of the bond, etc. So the picture on page 459 will be useful if you have things other than linear rotors. So when we have the linear rotor, we can think about, and I don't think we need to go through this just because this is what we already did back in chapter 8, our focus 8. So shows you how if you have a linear molecule, it only has 2 axes of rotation, because if it tries to rotate around the bond axis itself, no nuclei are moving. So the total J, the total angular momentum, would be Jx, so around one axis, and Jy around another. If it's a linear molecule, symmetric, then that I should be the same. So that would mean you have to have HH, you can't have like HCl. So based on this, it's saying that the I is the same. Or actually you could, sorry, because it doesn't matter which way you're rotating, it's still rotating the same atoms. So that isn't dependent on if it's symmetric. So let's just look at the rotational constant for HCl, which is one of the first self-tests. So the rotational constant, so if we want the rotational constant for HCl, then we have to start out by thinking, okay, so we have an A and a B, so this is H and Cl, and it gives us a particular isotope to deal with. So when we get the moment of inertia, we know that it's the reduced mass, because these two masses are rotating relative to each other. So it would be mass of the hydrogen times mass of the chlorine over the sum. And then we can use the bond length to figure out how far they are from the axis. So yeah, the bond length should be the same. What we're really saying, if we put the bond length in, and that's how we got the right answer, is that the H is rotating around the chlorine, which usually is a pretty good approximation. Chlorine is so heavy that you can think of it as a hydrogen rotating around. That way, it's the hydrogen's distance from the axis of rotation with chlorine that's going to be used for your R. So I figure out first the reduced mass. So they gave me the mass of the isotope for deuterium. This was given in the brief illustration above, the mass of the chlorine 35 isotope. So I get a reduced mass of 1.904. So the moment of inertia is 1.904. And then I'm going to change that into kilograms and multiply by the equilibrium bond distance squared. And I get a moment of inertia of 5.133 times 10 to the minus 47 if you're working in kilograms a meter squared. It makes sense, that's tiny. We're working in units that are usually used for bulk systems. So then our B will be h bar, which you get out of the table, 4 pi, moment of inertia, and we end up with 1.635 times 10 to the 11th 1 over seconds. So if you look back at how that fits into the energy expression, 1 over seconds will make sense as a unit for the rotational constant. So when you think about it, we're talking about a rigid rotor when we determined the energy back in focus 8. So a system that's rotating and the distance between the particles isn't moving. But you know that a diatomic any molecule, there's always vibration within the molecule. So as like something like HCl is rotating, it's also stretching and compressing. And so this first approximation is the rigid rotor. We determined that by the quantum mechanics back in focus 8, but you can't solve the quantum mechanics when you couple the vibration to the rotation exactly. So we make a correction to it. And this is a pretty good functional form for that correction. So it's Planck's constant times, this is a centrifugal distortion term. And so not only is it vibrating, but as it rotates faster, it's vibrating more. So how this term contributes gets bigger as J gets bigger. So the faster it rotates, the bigger the impact is on the fact that it's not a rigid rotor. So this distortion constant that we'll see in a little while, we can figure out with spectroscopy, and then dependent upon the rotational state that you're in. So you can also look at nonlinear molecules. So the only one your book looks at is a symmetrical nonlinear molecule. So looking at some of the examples show you that depending on which axis ammonia is rotating around, 2 of them are symmetric, 1 is not symmetric with those, so it would be a different moment of inertia than these two. So we're talking about molecules where two axes of rotation have the same moment of inertia and one has a different one. So when we look up at the top up here, it's showing us what our moments of, or what our axis of rotation is for each, and then what the moment of inertia is. So it can rotate about one axis, and then it can rotate in two different directions about other axes. So they're calling this one that's all by itself, the parallel one, parallel to that axis, and then these are perpendicular to it. So, yeah. So the parallel one, and then this can go this way, and this can go this way out of the plane. So we have two different moments of inertia. So when you figure out where this equation came from, you go through this that says that the energy is going to be the 3 angular momentum squared over their 2 times their moment of inertia. I did not put that on my sheet of paper. And so 2 of these are the same with the same moment of inertia, so we can group those together. And the J term then is different. And so when you come up here, or come to the next equation, you can say that the Jx plus Jy terms are really just total angular momentum minus the Jz squared. So angular momentum would be Jx squared plus Jy squared plus Jz squared equals the total angular momentum. And so this first term is just saying if I subtract this term from my total J squared, then I end up with the Jx and Jy terms that I had above. Then you just group them together. So in this last equation, they're then just grouping together the Jz's out, or the J by itself is out front, and now you have 2 Jz terms. And then if you group those together, you end up with a quantum number for the total angular momentum, and then a quantum number that's really in reference to the angular momentum about the axis that's unique. So the J or the K term tells you how much of the angular momentum is about this unique axis and how much is about the other two. So you could have it so that all of the angular momentum is about that unique parallel axis, and then K would equal J. Or you could have the opposite extreme where all the angular momentum is about those two that are equal to each other. So this way and then this way. And then that would mean that the rotation about that parallel axis has to be 0. So the J and the K deal with how much of the rotation is about which axis, and you have to have that distinction because they have different moments of inertia. So you use that equation the same way. You'd have to know all the information, so you'd have to know what are your axes to get your moments of inertia. And then you end up with, you end up with this equation back here when you simplify what's on page 462. So you end up with this equation so that your energy is a function of J and K, and each of those has a dependence on the moment. Sorry about that, I'm in the room with the phone. So each of these terms depends on the moment of inertia that you're talking about. So the moment of or the rotational constant with the moment of inertia that's unique. And then the second one is the one that's you have 2 of, and the unique one. So the K value really tells you the orientation of your rotation, and the J tells you the total angular momentum. So now we want to talk a little bit about the selection rules. So forbidden and allowed transitions. So this part on this part, I don't think it already gave us the selection rule. No. So this part talks about something that's way over our heads right now, but it's an important concept. So there are always limitations on what wave functions are allowed, which is the same thing as saying what states can a molecule take on. And depending on the spin of the nuclei that are undergoing rotation, you may have a wave function that's not acceptable for those. So if you have different nuclear spins, some of those states just aren't going to be allowed. So as you read through this, realize that this has to do with the statistics of fermions and bosons, and that it's an important thing to understand, but we don't really have enough of a physics background to understand that. Yeah, so the other thing we want to think about is a population of states. So it's always going to be true that your most intense peak in a spectrum from spectroscopy is going to be the peak where the ground state population is the greatest. So when we looked back at stimulated absorption and stimulated emission in our last section A, we saw that in each case, how much is absorbed or emitted depends on what the population of the starting state is. So when we look at that from Boltzmann's distribution, which unfortunately we're going to derive last in this class because it ties together quantum mechanics with thermodynamics. So we haven't covered this yet. It's actually in chapter 12. Nobody's covered it who's doing any order of the text. But it turns out that the population of any J state compared to the population at J equals 0 is always going to be an exponential function of that energy. So what we have in this exponent is the energy divided by kT. And what's out front is the degeneracy. So remember that for each L value, back in our discussion of atoms, so each L for an atomic orbital, you have different orientations that angular momentum can take, and those are the m sub L values. And so you're always going to have 2L plus 1. It's number of orbitals, but number of orbitals is really what the projection of that rotation or angular momentum is on some axis. So it's the same thing here. We have some total energy with a J value. J can be 0, 1, 2, 3. But the degeneracy, the number of those, the number of orientations that can take is going to be 2J plus 1, just like it was with respect to our orbitals. And so when we want to think about what's the most populated state for rotation, we have to take into account that the exponential term tells us they decreasingly are populated. So as the energy gets further and further from the ground state, that exponent gets more and more small, or big negative, which makes it a small number. But because of this degeneracy, which gets bigger as you go up, you don't just have the ground state as the most populated. So if you look at it, the J max for the most populated state, you can derive an equation that gives you what we have right here. So it's related to the rotational constant because that's related to the energy. And let's just look through the justification because it's an important concept. You're going to do a lot of this as you go along. So we'll start out in this justification so you can follow along on page 464. In order to find the maximum, we're going to take a derivative. So we take a derivative with respect to J because we want to find when that population of states is a maximum. And so if we take a derivative of that, and then it's just reminding you how to take the derivative of a product. So each of these is a function of J, so it's going to be the product rule. You could do that, or you could use Mathematica. but you end up then with this function. And now you want to set that equal to 0. So you want to say what j value makes this 0. And it's going to be, because even at j equals 0, this is 1. So the exponential part doesn't ever go to 0. So it'll be this first part. So if we look at the first part and set that equal to 0, we'll find the j at which this function for the population of states is a maximum. So well, not really, just back to our definition of what the population of states was. So I don't think I wrote that down. So just back to here that said the population of any one state with a j value relative to the ground state is equal to this. So that tells you here that if you solve for this j max as a function of your molecule's properties, the B, you will find the most populated state at what temperature you're working at. So that's something that's going to be important when you think about microwave spectroscopy. Because if you want to look at transitions, you want to make sure that you're not already in some highly excited state. And it takes so little energy that it's often a good idea to do microwave spectroscopy at low temperature. Because if you look back at that exponential, it has 1 over temperature in it. So as temperature goes up, that term goes down, and you have more populated states in the ground state. So when we look at microwave spectroscopy, so now using what we just talked about for the first 20 minutes here, about the energies of rotation, microwave spectroscopy takes advantage of adding energy to excited rotation. And the first important selection rule is that the molecule has to be polar. It's essentially like thinking of how do you get a grip on the molecule with an electric field. So if you have a molecule and you pass electromagnetic radiation through it, the only way for it to interact is with a charge change. So if it has a polar nature, you'll be able to add rotational energy to it. And so another one of the selection rules is that delta J has to equal plus or minus 1. And that comes from what we've discussed earlier, and that is that a photon has angular momentum of 1. So if it interacts with a molecule, it can only either add 1 if it's absorption spectroscopy or subtract 1 unit of angular momentum. And then delta K has to be equal to 0. And I remember why that was, but for a second I'm drawing a blank. I will have to relook at this. I can't remember why delta K that you can't change the rotational energy about the parallel axes. I can't remember that right now, sorry, and I'm not seeing it clearly, but those are your 2 selection rules, along with the fact that the molecule has to be polar. So now we can look at that limitation. So if we look at then what should the frequencies be, they're going to be the difference in energy between any J state and an adjacent one, because J can only change by 1. And so the difference in energy between 2 J states that differ by 1 is equal to 2 is equal to 2HB times J plus 1. So that means that if you change this into units of frequency, the frequencies that you should see, get rid of the H, should be 2, your rotational constant, J plus 1. And if you have a non-rigid rotor, this term will also be in there that is for that centrifugal distortion. And so this allows you to figure out both the B and the D. So if you look at the frequencies from your spectra, divide each of them by J plus 1 because of this cubed right here. Then this first term has no J plus 1. This term goes from a 3 to a 2. And so if you do a nonlinear fit and look at what you get, the D will be essentially, well, no, you don't have to do a nonlinear fit. You just graph this whole term versus this whole term, and it'll be a linear fit. So if you graph the frequency of your transitions divided by what quantum number plus 1, you graph that against, on the x-axis, J plus 1 squared, the slope of the line will be 4 times that centrifugal distortion, and your intercept will tell you the B value. So by doing microwave spectroscopy, you're able to get both of those properties or parameters about your molecule. So when you look at this I thought was a little confusing. When you look carefully at figure 10, realize that they're not saying that the transitions are all the way from J equals 0 up to J equals 5, etc. That each of these lines has black up to where it starts, and then red from where it starts to where it finishes. So each of these is 0 to 1, 1 to 2, 2 to 3. So those are each of your transitions that are taking place that you'd be graphing the frequencies of those transitions. So if you have a molecule that doesn't have a dipole moment, you can't use just plain microwave spectroscopy where you absorb energy to excite it, but you can use Raman. So remember, Raman spectroscopy takes advantage of the fact that light can be scattered, and then as it interacts with the molecules that it's being scattered from, it sometimes can increase their energy and sometimes decrease their energy. So in order for that to happen, you have to have a difference in polarizability within the molecule. So this picture at the bottom is a good one. So if you think about it, when you look at rotating this molecule, it's going to rotate over to this side and back as it rotates round and round. When the electric field is coming through this way, it's going to have a different ability to polarize than if the molecule is perpendicular to the electric field. So the polarizability is changing, and so that means that you'll be able to interact and do Raman spectroscopy. So it's the same concepts. In Raman spectroscopy, you're still looking at the same energies and changing in those same energies, but you're doing it in a different way. You're doing it by scattering light and then either increasing your frequency or decreasing your frequency. So the picture on the bottom here shows you that you have a frequency of light in the middle. So that's your Rayleigh scattering, where it scatters without changing the energy. If it scatters by increasing the energy, then that means you forced your molecule to give up some rotational energy and add it to your photon, versus if the energy if the frequency gets smaller, then that means your photon excited the rotation of the molecule and was still scattered, but came off with a smaller frequency. So I think that's all I want to say about rotational spectroscopy. So that's microwave, takes the smallest amount of energy. The next thing we'll talk about is vibrational spectroscopy, which is next on our scale of how much energy it takes.